Hi, this is the second part of thermochemistry, and we're going to start with something called enthalpy. Enthalpy is the measure of energy that is released or absorbed when a reaction takes place. You get bonds that get broken first, and so as the bonds are broken, energy is absorbed, meaning you need energy to break up bonds. And then as new bonds are made, energy is released. And then the difference between these two determine whether or not a reaction is endothermic or exothermic. And we've learned this before when we talked about Le Chatelier's principle. But if your delta H, which is what enthalpy is, comes out to be negative, then you have an exothermic reaction. If your delta H for the reaction comes out to be positive, then you have an endothermic reaction. And so the first thing we did was to learn one way to find delta H, or find enthalpy, and that was using something called Hess's law. Hess's law says if you have a bunch of reactions that take place in a series of steps, that you can simply add the steps together in order to figure out the overall enthalpy for a reaction. So basically you're going to add the steps together. What makes Hess's law unique is that you sometimes are given the reactions, but they're not in the right order. So if we were using this data below here, and we were trying to get this overall reaction of 2 carbons plus an oxygen makes 2 carbon monoxides, and we were given to the 2 equations below here. And so these 2 equations need to add up and equal this equation here. So I got to figure out a way to take these 2 equations and get it to equal the top one up at the top. So this is my goal. This is what I'm trying to get to. Right there. Excuse me. So if you look, you can see the carbon here, this solid carbon, and you can see the solid carbon here. The difference is they're both on the reactant side, so that's good. But the problem is that this one has a 2 in front of it and this one does not have a 2. And nowhere else do you see a carbon to combine another carbon to make it 2. So in order to get the coefficient of a 2 with this carbon down here, because I'm going to combine these 2 and make it equal that, I need to multiply this by 2. So I would multiply this by 2 all the way across. When I do that, I also need to take this and multiply it by 2. Now I'm looking at my oxygen, so that'll help my carbon. You can see oxygens are in multiple equations, so I'm going to kind of leave the oxygens and see, hopefully they'll just fix themselves here in a minute. So now you see the 2 carbon monoxides. Do you see carbon monoxide down below anywhere? Carbon monoxide is in the second equation here, but do you notice over here it's on the product side, and over here it's on the reactant side. So it's on the wrong side of the arrow. There's no equilibrium here, so it's not going back and forth. So what we're going to have to do with this equation is we're going to have to flip this equation around in order to get the carbon monoxide to be on the correct side of the arrow. So if I flip this equation, so I'm going to flip it, so I'm going to write flip over here. When I flip it, I'm going to end up changing the sign. Right now this is an exothermic reaction, but if I flip it around, it's going to be an endo. So I'm going to change the sign here on my equation to a positive. So I'm actually going to flip it around. I'm going to write it up here before we can see it better. So we are going to have CO2 now over on the reactant side, and I'm going to have carbon monoxide gas and 1/2 oxygen over here. So I've flipped it, and so I'm going to mark through this one before I don't look at it anymore. So I flipped it, so then I changed the sign when I flipped it. Now there's got another problem with it. Do you see how the carbon monoxide here has a 2? Well, this carbon monoxide does not have a 2, and there is no more carbon monoxide to go with it. So I need to multiply this one by 2 as well. And when I multiply 1/2 by 2, it makes a whole. 1/2 multiplied by 2 makes a whole. So I'm just going to erase that right there. So I multiply this equation by 2. So I'm going to put times 2 here as well. So now to see if I've done all this right, I'm going to combine my number 1 equation and now my new number 2 equation and see if it equals my goal that's up there. So I've got 2 carbons, and do you see 2 carbons anywhere else? No, so they're going to come down. And that's going to be a solid. It's pretty messy there, isn't it? So 2 carbons as a solid. Okay. Do you see there's 2 oxygens here on the left, and there's 1 oxygen here on the right. So the fact there's 1 on the right and 2 on the left, you're going to be left with an extra O2 on the left. And now we go to this. We have 2 CO2s on the right and 2 CO2s on the left. This is known as an intermediate. These will cancel out with each other. There's no carbon monoxide to cancel, so we'll just bring that down. And we had already canceled him out with that guy up there. So you can see, yes, this equation now is equaling my top equation. So if that is the case, now I could just take these things that I've got, multiply this by 2, multiply this by 2, and add these 2 together. That's all I'm going to do. When you add those 2 together, you should be coming out with a negative 221. There is 1 decimal in those. Since we are adding, we do look at decimal places, so it would be 0.0, and the unit would be kilojoules. And so there's my answer. So there's a worksheet for Hess's law. And the first year that I copied it, which is this year, I had made a mistake on number 5. So number 5, I've uploaded the corrected version for number 5 on Google Classroom. So number 5 on the worksheet for Hess's law had a problem, and I have fixed it. So if you want to get the corrected version, it is on Google Classroom. That's Hess's law. And then we went through very quickly some vocabulary. The enthalpy of vaporization is the amount of energy it takes to convert a liquid to a gas. Enthalpy of fusion would be the amount of energy it would take to melt a solid. And then we have something called standard heat of formations. Heat of formations is the amount of energy it takes to make 1 mole of the substance from its pure elements. So for pure elements, the most stable form of the element, the enthalpy of formation is going to be 0 because it doesn't take any energy to make oxygen from oxygen. It takes energy to make water from hydrogen and oxygen, but it doesn't take any energy to make oxygen from oxygen because oxygen is oxygen. And then I wrote the most stable form of carbon is graphite, because we will see carbon from time to time, and he's in different forms. Because it does take a lot of energy to make carbon into diamond. So, but carbon in its purest form is graphite. So we did not get a chance to do this, but we'll try to do this tomorrow. But the formation of ethanol. So ethanol is C2H5OH. That's an alcohol times 2 plus 1 add an OH. This would be made from carbon, and it would be made from hydrogen, which is H2, and it would be made from oxygen, which is O2. And the definitions of heat of formations. Heat of formations is that it is, here's the key word here, 1 mole. So that means this has to stay a 1 in front of that there. So 1 mole of that. So we would balance accordingly, and we actually get to use fractions with this. And so for carbon we would put a 2. There are 6 hydrogens here, so we would put a 3. But there's only 1 oxygen, and the way we would make 1 oxygen, we would put 1/2. So the definition of heat of formation is forming a substance, writing an equation from its elements, so from the pure elements. So heat of formations are pretty easy. In your back of your book in Appendix C, there's a whole list of heat of formations for all kinds of substances, and we'll be using those heat of formations to do our calculations. So in just a minute, when I pull numbers for this equation, you will know that I am pulling these numbers from Appendix C in the back of your book. And so that's where you'll go to get your numbers. For your first homework, I've given you a chart that does have the heat of formations. The one worksheet is missing carbon monoxide, so you will have to look that one up in the back of your book. So this is the formula. We did do this formula in pre-AP. And this crazy looking thing means the sum of. This is called sigma, and it is a Greek letter, and it means to add up all. So it means to add up all your products, and this means to add up all your reactants, and then we're simply going to subtract them. The little n and m means to multiply by the coefficients. We did, again, do this in pre-AP, so hopefully this looks a little familiar to you. So we did this first sample problem. It says calculate the standard enthalpy change for the combustion of 1 mole of benzene. So our first thing we would want to do is write a balanced equation for the combustion of benzene. And they're asking for us to find 1 mole of benzene. So I'm going to use 1 in front of benzene because they're saying combusting 1 mole. A combustion always requires oxygen, and it always makes carbon dioxide and water. And then I would balance accordingly. In front of my carbon there are 6, so I'm going to need a 6 here. For hydrogen there are 6, so I'm going to need a 3 here. And there's 12 oxygens here and 3, that's 15. And you're allowed to use fractions, so this would be 7.5. So there's my balanced equation, and again, the only reason I'm doing 1 mole, they asked for 1 mole of the substance. If you did it for 2 moles, you would end up dividing by 2 to get 1 mole. So that's another way we could have done it. But we can use fractions, believe it or not. I am going to allow you to use fractions on this. So we're going to use the sum of the products, which these are our products. I'm going to use the water as a gas because it does matter, and you're going to want to pay attention as you read problems whether it's liquid or gas. I pulled the gas number from the back of the book, so I'm going to use that as a gas. This is also a gas. This is a gas. And this is a liquid. So I pulled the numbers from the back of the book for carbon dioxide. So to find the delta H for the reaction, which is what RxN stands for, I'm going to add up the sum of these guys. So I'm going to take my 6 and I'm going to multiply it by carbon monoxide, which I'm going to find in Appendix C in your back of your book under the delta H category. And it is negative 393.5 kilojoules. Again, from the back of the book. And then I'm going to add to it, because this crazy symbol means sum of 3, going to use his coefficient, water molecules. And so I go to the back of the book, and I'm going to find water as a gas, because that's what I looked it up as the other day when I did it. You're going to get negative 241.82 kilojoules. And then you're going to subtract the sum of, and so I'm going to add up this side here. So we've got 1, so I'm going to multiply 1 times the benzene, which is 49 kilojoules. And then I would add to it 7.5 oxygen. But oxygen's a pure element, and pure elements don't have any heat of formation, so they would be 0. So this would just cancel out. So I would just simply multiply these, add them together, and then subtract this side to find the heat of the reaction. And this one comes out, we would use sig digs, we are adding, so it's the least amount of decimal places. Our 49 does not go out any decimal places, so our answer is not going to go out any decimal places. You would get a negative 3,135, and then the answer would be in kilojoules. It technically is kilojoules per mole, since that's what we've done. These are kilojoules per mole, because these are mole ratios that you're using to multiply. But I'm okay if you just put kilojoules. And there is my correct answer. This is an exothermic reaction. We can tell because it's releasing energy there. And so that is our first lesson that we studied. We studied specific heat, Hess's law, and then we did enthalpies using the enthalpies of formation. If you need help, please come in and see me.